As we start Chapter 4, we're only doing 2 topics in Chapter 4, 4.1, and I believe 4.3. So what we're doing in this chapter is solving systems now of linear equations in 2 variables. So in Chapter 3, we only took 1 equation at a time. In Chapter 4, since it's systems of equations, we're going to take 2 equations at a time. Now, suppose our first equation is this blue line. It's positive slope, and it has an infinite number of points all along that line. And if we took a second equation, and when we put it on a graph, it's this black line. Now we know this one is negative slope, and there's also an infinite number of points, coordinate pairs, along that line. But a unique thing happens right there. That is, these 2 lines intersect, and there is an ordered pair right there that has an x value and a y value that is a solution for the blue line and also a solution for the black line. So when this occurs, when we're dealing with 2 equations, systems of equations that intersect at that unique point, we say we have solved this system of equations simultaneously by making a graph and then identifying that point, which looks like about a -1 and a 1. Now another scenario might be that we have the blue line, which is a graph, and the black line, which is a graph. And, well, these are equations on a graph. Now, they appear to look parallel, and they are. They have the same slope, but different y-intercepts. Would these equations, if they are parallel, ever intersect? And the answer is no. So for this, there would be no solution. And that's what we would state. Now, a third scenario would be if we drew the black line. And I tried to show this here, that we drew the blue line actually was right on top of the black line. In fact, the equations were the same. Well, remember, there's an infinite number of points along each of these lines. And whatever is the solution for one is the solution for the other, since they are identical. So we would write this and say there's an infinite number of solutions for this scenario. And we usually write this one in set builder notation. X comma y is such that, and then you list one of the equations. And this is what we'll be doing. Now, another type, as we actually get into a discussion of what we're doing here, looking at this first graph, and this deals with a company that's producing something, and we actually have 2 equations here. One of them is called a cost equation. We write it in function notation. Cost is such that, and then we have usually some fixed prices of a certain item plus some basic costs. In this case, it's going to be like 10. That's where it's starting here. And then we have a revenue function, where we sell each item for a certain price, and that would be right there. And then if we multiply it by the number of items that we sell, that were sold, this is money that we're going to take in. This is money that it's going to cost to make an individual item, plus some other kind of expense. So we are finding that as we plot these, they intersect right at this point. So what does that mean? Well, that this ordered pair would be a solution for your cost function, and would also be a solution for your revenue function. This is where they intersect. This is a break-even point. That above it now you're going to make more money, and in a sense this is profit up here, than your actual cost. And that's what they're describing here, the break-even point. And you could read more about it. So again, that was an example of systems of equations. Here are 3 more examples of systems of equations. And we're looking for that unique point where they would intersect, where that would be a solution for both. Now, as we illustrated here, you could find the solution by graphing, and then later we're going to find them by using algebra. So what are they asking us in Objective 1 and Example 1? We want to determine, is this ordered pair a solution for both of these equations? And how do we do that? Well, we put the x, replace the x with a -1, replace the y with a 1 in both equations, and see if it ends up with a true statement. And we would do the same thing here. So this is substituting your x value, your y value into the equations. Now for letter A, putting the 1 for the x and the -1 for the x and a 1 for the y ends up in a true statement for the first one, and also a true statement for the second one. And the work is here. Now, when we look at the second equation, when we put the -2 and 3 into it, the first one is true. But when we put that same -2 and 3 in the second equation, it's false. So this is not a set of ordered pairs, or a member of ordered pairs, that would make both equations true. That is the point where they would intersect. And you'll be doing some of these in your lab as well. Now here we have 2 equations, both in standard form. And you might say, what technique might you use to graph these? Well, for the first one, I think I'd use a x and y intercept t-chart. So here, if x is 0, y is 2. And if y is 0, x is 2. So I'd plot that on my graph. A dot right there, and a dot right there, and that's the blue line. Then I would solve this, let's say for y. Transpose the y, and I'd get y equals 3x. Transpose that to a 2 to the other side, and now rewrite it so we could read it better. Y equals 3x plus 2. So when I graph this, again, my y-intercept is 2. Oh, that looks like a point of intersection. And my slope is 3 over 1. So I would go over 1, up 3, right there, and that would be my second line. And you see they intersect on the y-axis at the point 0, 2, which happens to be the y-intercept. So you're going to be using your graphing skills from chapter 3, and this is the first kind of problem other than seeing if an ordered pair is a solution for both. In the old days, when we did the graphing by hand and we used paper, sometimes just being a little off, you wouldn't get the point of intersection. But using MATLAB and their super accurate graph, that is not a problem anymore. One of the words we want to associate when there is a point of intersection, we say the ordered pair is a system at least one solution. It has at least one solution. It is said to be consistent. If it has at least one. If it has infinite, it's very consistent. And more vocabulary is if it has at least one solution, one point of intersection, it's consistent. But were these equations the same? No, they're different lines. We say the equations are independent. Now, if you recall from that first set of 3 graphs, if the lines were on top of each other, they would be dependent equations. And those answers would also be consistent because there's an infinite number of answers. Okay, we're now going to take a look at example 3, in which we're asked to graph these. Let's raise it up a little. Now, when we would put these either in slope-intercept or standard form and graph it, whatever technique, and we did some of this in chapter 3, that is, if we solve both equations for y, we would see here the slopes are the same, but here this y-intercept is -2, and down over here you may recall it was 0, that is, it went through the origin. So when the slopes are the same, the y-intercepts are different, the lines are parallel. So would there ever be a point of intersection, as we said? And the answer is no, no solution. Now in this case, we are saying the equations are inconsistent because there is no intersection, or at least one ordered pair that's a solution for both equations. And this would be another one. So summary of this, if you work the equations, solve them for y, if the slopes are the same. Now again, they're asking you to graph this, so you have to graph both equations to get the credit. But if they turn out to be parallel, then there are no solutions. Now another type, in example 4, if you made a graph of these, you would see actually that the lines come right over one another. In fact, one of the things we're going to show you very shortly is that if you multiply this second equation by a 2 that we're allowed to do from chapter 2, we get here 2x plus 4y equals 10. And that's exactly what this equation is. So it's disguised a little bit, so you have to fiddle with them a little bit. Now, since every ordered pair that is a solution for this one is a solution for that one, since they're basically the same equation, there is an infinite number of solutions. And we say that these equations are dependent. And we write the answer in set builder notation. You can use either one. Now in MathLab they'll give you 3 little boxes to choose from. One will be an ordered pair that you put in. That'd be consistent. Another box would be no solution. And a third box would be set builder notation. And you're going to choose which one. Now in most cases it'll be a consistent, unique ordered pair. But you need to keep in mind these others. And again, they're going to ask you to graph these. That's how we solve the first few. And we'll be doing some practice in a little while. So in summary, this is a consistent system. It has at least one solution. There's an infinite number. And the equations are dependent, since they're the same equation. And lo, the book now is summarizing what we did in our initial introduction. Okay. Now, there are other methods of solving systems of linear equations, and we say graphing. But again, if you were doing this by paper, just being off a little bit, it would be hard to get the exact spot of intersection. And if your coordinates were fractions, that would be hard to pick out. So are there other methods? Well, very definitely. And the first other method than graphing that we're going to look at is called substitution. Now as we see this equation's in standard form. Now the second equation, it appears that they solved for the letter x. So that's a key thing. And what we're going to do, as you will see, is take this value for x and put that value in the other equation where the x is. That is, substituting this value in terms of y where that x is. And that's what they're showing you down here. So we'll raise it up so you can see this better. So this x, we're saying, is equal to 2y minus 5. Now we're going to distribute this. And now we have an equation with only one kind of letter, the y. We combine like terms, we transpose this, and we divide both sides by 8. So we get y equals 4/8. That reduces to 1/2. So now you have one of the members. So we're saying y is 1/2. Again, that would be hard to pick out on a graph. So now what do? Well, we say y is 1/2, so we use the other equation. We want to now solve for x. So 2 times 1/2, which is our y value, which we're getting right there and putting what it is, minus 5. So when we do this multiplication, the 2's cancel out, and we just get a 1. So 1 minus 5 is going to equal negative 4. So your second member of the ordered pair now is a negative 4. And this should be the ordered pair where these two equations intersect if you were to draw them on your graph. So doing what we did on the previous page, we're substituting where the y is the 1/2. This gives you a 1. 1 minus 5 equals a negative 4. There is my ordered pair. Now when you put this in the math lab, you have to be sure you put it in parentheses, and there is a comma separating the two coordinates. Now they're giving us a little summary here of how to do substitution. You have your two equations. You want to solve one of the equations for one of the variables, for either x by itself or y by itself. Then you take that value, put that in the other equation for the letter. If you solve for x, you're going to put that y value there. If you solve for y, you're going to put that x value there. And we'll see that here shortly. Then you find what one variable is as you solve for it. Then substitute back in the original equation to solve for the other variable. And a good idea is to check your work to see if it is a solution for both of the original equations. Now if you're using MATLAB to do it, then you can just check to see if you've got it right by putting your answer in. But if it's on a test, you may want to physically check it, because you don't see your answers until the end. Okay, let's take a look at example 6 here. Now as we look at this, we see these equations are loaded with fractions. So the first thing you want to do here is get rid of the fractions. So for this one, I would multiply everything by 6. And this is a technique from chapter 2. And for this one, I would multiply everything by 12. So when I do that, my new equations become this. Now there is an x all by itself. So I like a nice positive x. I'm going to take this x, put it over to this side as a positive x. Take this positive 3, move it over as a negative 3. And now wherever x appears in the other equation, right there, I'm going to substitute that. And that's what they're doing here. You can't see it all, but we will shortly. Now, once you've done that, multiplied through, you get y equals 3/10. Now, you don't have to use the original fraction form. Let me just do this one. It'll be negative x plus 3 times y, we said, is 3/10 equals 3. So we're using this one here. We're substituting our y value where the y is. Now for something like this, let's do the multiplication. We get a negative x plus 3 times 3 is 9 tenths equals 3. Now let's get rid of the fraction as we did over here by multiplying everything by 10. So this is a negative 10x. Here the 10's cancel out, plus 9 equals 30. I'm going to transpose my positive 9 to the other side. Get a negative 9, so this is going to be 21. A negative 10x equals 21. Now I'm going to divide everything by a negative 10. And negative 10. Don't forget that negative. This becomes an x. So our ordered pair should be 21 tenths, a negative 21 tenths, and a 3 tenths. Now I haven't looked at the text. I hope I'm right. And I am, and there it is. Okay, so when you have fractions, what you would do is multiply each of the fractions by the lowest common denominator, get rid of the fractions, and then you have an x value. Okay, so far we have two methods of solving. Graphing, which would be really tough for these fractions, but showing you the kind of thing that's going on to simultaneously solve these equations, and the substitution method, where you solve for one letter, then use that other value in the other equation, substituting. Now there is another method still, and this method is called the elimination method. And there is a protocol for this, and it's showing you nicely here how to do it. So step 1 in the elimination method is we put the equations, if they're not already in that form, in standard form. Now, we make a quick study of the equations. If we were to add them up, would one of the letters be eliminated? And here, yes, the x's would cancel out and give you a 0. But then you add up the other stuff. A negative 5y and a positive 1y is a negative 4y. And adding this up, you get a negative 8. Now we're going to divide both sides by a negative 4 right here. Negative 4 there. And a negative 4 there. And we get y is 2. Oh, we have one of the members. So we can use either equation, usually the easier one, which they're using this one. You're going to put the 2 where the y is. Now you're going to subtract 2 from both sides, or transpose. And then you get negative x equals 2. But you want a positive x. Well, you can just divide both sides by a negative 1, or just change both signs. So again, negative 2, 2 is your ordered pair. Now remember, since they are an ordered pair, you can't decide to reverse them. You can't say, well, this is negative 2, I'm sorry, this is 2 and this one's negative 2, because that wouldn't be a solution for these equations. It must be this order. Now, how many papers have I checked over these years where the student at this last stage just says that this is 2? Again, putting a 2 there for x gives you a value for y, but it's not correct. Now, if I see you did a lot of the work, though, on your blue sheet, I'm able to give partial credit. So a quick review, we line them up, standard form, the x's cancel out, we solve for y. Once we find a y, we put that in the other equation and get what our x is. And we're careful to list it in the proper order. This is an ordered pair. So you can't put there 2, negative 2, even though the numbers are the same. Since order is significant, you can't flip them around. Now we'll do some others. So a summary, you rewrite each in standard form. Now in this next one, you'll see that we may have to modify one or both of the equations so that one of the letters cancels out. We solve for that letter, put the value back into the equation, solve for the other letter, and then check. So let me do letter 8 for you and show you a protocol of how to do these. And take some notes on them. So I've just written them out as they are here, checking that I copied it correctly. Now notice if I put a line underneath this, adding them up, nothing's going to cancel them out. So I have to modify these equations so something would cancel out. So here's how I do it. I put a bracket, and if I multiply this equation by 4, and then this equation by a negative 3, here I'll have a positive 12 and a negative 12. These will cancel out. So normally I like to put this over to the side, but I see I'm not going to have enough room. So I'll just do this and bring it down here. So this is going to be 12x minus 8y equals 40. Now this one, again, I'd like to have it out here, but this is going to be a negative 12x. Remember, that's a negative 3 times this. Now negative times a negative gives me a positive here, 9y, and then negative 3 times 15 gives me a negative 45. Now when I put my line, these will cancel out. And when I add this up, I just get a y. And when I add these up, I get a negative 5. So my y, as they are indicating down here, is a negative 5. And as I did look at this particularly, but I see they have solved for x first, which is another way of doing it. I chose to get rid of these. You can get rid of those as well. But now we have y is a negative 5. So let's use our first equation. 3x and then a minus 2 times a negative 5 equals 10. So now I clear parentheses. 3x plus 10 equals 10. Now I'm going to subtract 10 from both sides, and I get 3x equals 0. Or I could transpose. Divide both sides by 3 now, I get x equals 0. Now notice they got the x first. I just, there's two ways to do it. You get the same answers, whether you solve for one letter first or the other. So the key is your ordered pair then is 0, comma, -5. And we use that particular technique. Now in example 9, again, here's a set of equations. This one contains fraction. So I'm going to multiply everything here by 2. So when I do it, I get this. And I don't know if you can see what's happening here. We're almost cut off. But when I add these up, this is a 0. When I add this up, this is a 0. And when I add this up, this is a 1. Now, does 0 equal 1? And the answer is no, this is not true. When algebraically you do something and you get a not true statement, this indicates that the original lines were parallel. So there is no solution. Now they didn't look like they were parallel initially, but if you were to solve each of these equations for y, you would see that the slopes are the same, but the y-intercepts are different. Ah, those lines are parallel. And on the next page, they tell us. Now another way to write it is that there's no solution. There's an empty set, or the symbol for no solution. Now in example 10, it's similar to what we've done. Now if we multiply this first equation here by a 2, everything by a 2, and we want, let's say, the x's to cancel out, this will become a -10, this is a +10. Notice what happens to everything here. This becomes a -6y, that will cancel. This becomes an 18, and this is a -18. So when we add them up, it's 0 equals 0. Is that a true statement? Yes. When you have a true statement, it indicates that the lines were actually, let me just do it this way, that was one line, and the other line, which is the same equation, was right on top of it. So for this one, there is an infinite number of solutions, and we write it and just take either of the equations. X comma y is such in set builder notation. You could use either one, because in a sense these are the same equations. If I multiplied this equation by a -1, it would make it exactly the same as this. It's disguised here a little bit, but when you do the math, the algebra, this is what you get. And again, if you had a graphing calculator, there are ways to put your data into a graphing calculator and actually get a graph to see if it's going to intersect in one place, whether they're parallel, or whether the same line. And there's our vocabulary check, and we're asking to match up these with what we have here. Okay, we'll get on to our mini lecture right now.